So I'm going to cheat a little bit with this movie. I'm going to use it as the first movie for the Molecular Structures 2 extension, but then we're also going to come back and use this same movie when we start talking about alkenes and alkynes, and you'll see why when we get there. Whichever way we approach this, what we're starting to do with this movie is we're starting to think about the electrons in molecules. Because in the same way that electrons in atoms determine the properties of those atoms, the electrons in the molecules determine the properties of the molecules. We're going to start off nice and simply and apply the so-called Born-Oppenheimer approximation. And we're only going to ever mention this once in this course. But what the Born-Oppenheimer approximation says is that if you want to think about the electrons and if you want to study the electrons, don't worry about what's happening to the nuclei. The behavior of the nuclei is very different to the behavior of the electrons. Nuclei move more slowly, they have way different energy levels and so forth. So if we want to think about the electrons, we can do that just by thinking about the electrons. Now let's start off very, very simply and think about a typical covalent bond. In a covalent bond, we're looking at the electrons, and we're going to say that those are shared between two atoms. So those electrons are going to be localized between the two nuclei of those atoms. In other words, we can say approximately where we expect the electrons to be. In the same way that way back with atoms, we could talk about approximately where we expected the electrons in atoms to be. Now with atoms, we said that the electrons would be probably in the volume described by atomic orbitals that had particular shapes and energies. Well, we're going to do the same thing here and talk about molecular orbitals, and in this particular case, bonding orbitals, which are formed by just overlapping the atomic orbitals. If the electrons are probably going to be in the atomic orbitals, let's overlap those atomic orbitals to describe how they're probably going to be in the bond. So let's take two very simple ones, a couple of s orbitals. Right here, they're in separated atoms, but now let's bring those atoms together to make the molecule. And as we do that, the orbitals will overlap. There's nucleus 1, nucleus 2, and here's the overlap of this 1s orbital and this 1s orbital. We've said very, very simply, when we got the bond, the electrons will probably be in this area here between the two nuclei. We're going to call this a bonding orbital because it's where the electrons are probably going to be in the bond. And we call it a so-called sigma bonding orbital. Now, right now, the distinction's not going to necessarily mean very much, but a sigma type molecular or bonding orbital is one that includes the line between the nuclei. So you can see there's the line between the nuclei, and this bonding orbital contains that. Now, of course, what we've always said is that when you bring atoms together to share electrons, then you get a lower energy and more favorable situation. So let's think of the energy. Yes, the energy of those original s orbitals. We bring them together to make this orbital here, and the energy of an electron in this orbital will be lower. And this is how we would draw this. Some people call this a correlation diagram because it correlates which bonding orbitals go with which atomic orbitals. I just like calling it a pretty picture, but essentially this is our old bonding model. One electron in this atom, one electron on this atom in these orbitals. Bring them together to make the bond. The two electrons will be in there in a lower energy situation. So if you follow that, you understand bonding orbitals. Really, really very easy. You're going to make a bond, you bring the two atoms together. Each atom has its atomic orbital that had an electron in it. Those atomic orbitals overlap to make a bonding orbital, and both electrons are probably going to be in that bonding orbital. Now we can take this idea, the overlap of atomic orbitals, and really have fun with it. It's not limited to s orbitals. We can think about p orbitals as well. Now, of course, you'll remember that there are 3 different p orbitals in any p subshell, all at 90 degrees to each other. So I'm going to define my axes thusly. Z is along the horizontal, X is vertical, and Y goes in and out. So the pz orbital look like that. There's the z-axis, there's the z-axis, atom 1, atom 2. Bring the atoms together, the pz orbitals overlap, and think about how it will overlap. This lobe here and this lobe here will overlap nicely, and you'll have this different shaded lobe sticking out there and this different shaded lobe sticking out there because, of course, they were not involved in the bonding. Does that make sense? Now again, we call this a sigma type orbital, making a sigma bonding orbital, because again it includes the line that goes through the nuclei. And we can draw the same energy level diagram again, except now it's electrons in a pz orbital on each atom. As the atom comes together to make the bond, you've made that sigma bond. That orbital is going to be lower energy than either of the original pz orbitals. We can also, although we won't see this too much, an S on one atom can overlap with an S on another, or the S on the first atom can overlap with the pz on the other atom. Must be the pz. We'll see in a minute why it can't be the px or the py. So that p has to be the one in the correct orientation. It has to be the one that is pointing at the s orbital, just like this. Bring them together, and there is that nice little overlap. And again, it's going to be a sigma orbital because it contains the line between the nuclei. And again, we can draw pretty little pictures, although they again, now I've got it labeled S, I've got it labeled PZ. Either way, because they're overlapping, if there's an electron in each of those atomic orbitals, now those can be shared in the bonding orbital. Now it's important to note that you have to have the right orientation. Okay, you can have the S and the PZs interacting, but they can't interact with the PX or the PYs on a different atom because there's not the right type of overlap. For example, if we take here an S with a PX and try and bring them together, now the overlap, and it's very important, I haven't necessarily pointed this out yet, it'll become more and more significant as we go through, but you have to have a little match of the so-called signs. Remember, atomic orbitals are described by wave function because they're waves, and waves can be positive or waves can be negative. The way I've drawn this here, clear means positive, and the shaded means negative. So the clear here can overlap here with that clear, but it would have a zero overlap up here because the clear cannot overlap with the shaded. So this can't overlap, and nor could this overlap, because again, while you got some clear overlap possibilities down there, you got clear and the shaded here, which would negate the clear and the clear overlap. One of the things that's important with atomic orbitals is they have to have the right level of overlap. So we've seen s orbitals, those spheres, overlap to make sigma bonding orbitals. We've seen pz that point at each other overlap to make sigma bonding orbitals. We've seen s and pz overlap to make sigma bonding orbitals. Well, what if the orbitals don't point at each other like the pz's did? Well, no problem. If we think about here px's, so we've got px on one atom, px on another atom. Px orbitals are parallel to each other. So as we bring the atoms together, we'll bring the shaded part and the unshaded parts together so that they can overlap. There's the shaded overlapping. There's the unshaded overlapping. Okay. What's important to note here, though, is that while this is a bonding orbital, because an electron can be there and it can see the two nuclei, it could be there and see the two nuclei. It's not a sigma type orbital because here's the bond, or the line that goes between the two nuclei, and you can see that our orbital is not including that line. It's above the line and it's below the line, but it doesn't include it. Now this means that again it's a bonding orbital, but we call it a pi bonding orbital. Sigma must include this line. Pi orbitals don't include that line. They have a so-called node. They have zero density around that line that goes between the two nuclei. Okay, now we can draw the same energy level diagram. Electron in a px, electron in a px come together, two electrons in a pi bonding orbital that is of lower energy. And finally, how about the PYs? Well, these are harder for me to draw, but hopefully you can imagine it. Here's the shaded bit pointing at you, the unshaded bit pointing away from you, shaded bit pointing at you, unshaded bit pointing away from you. Bring those together to overlap and we get this type picture. There's the shaded now, that's combination of those two ones coming out at you, the unshaded that's going away from you because it's a combination of the two unshaded going away from you. This is actually just a 90-degree rotation of what we saw with the PX ones. Same idea though, the line is kind of going between these, but it's not including them. So they're pi orbitals, and again, when an electron each in py orbitals on an atom overlap, they make a pi bonding orbital that can have two electrons in of lower energy. Well, so what you say? Well, you can now explain all kinds of fun things with the bonding. A sigma bond is a normal bond. Okay, I didn't really emphasize that too much on the first slides, but hopefully you can appreciate when you've got two atoms pointing at each other, their orbitals overlap nicely between the two nuclei, include that line between the two nuclei. That's what you think of for a bond. So a single bond is a sigma bond. But a double bond is a combination of a sigma bond and a pi bond. Let's look at this here together. Essentially what I've got here is I've got a lobe or an orbital on this atom pointing directly at an orbital on that atom. So when I bring those together, those can overlap to give me a sigma bond, excuse me. And then I've got the PX here and the PX here. Bring those together and they will overlap to give me a pi bond. So the combination is I have a sigma bond, that was the overlap of those two, that's a normal single bond, and then I have two electrons in that, and then that orbital is full, because remember you're going to put two electrons in an orbital, but now I've got this pi bonding orbital above and below, in which I can put two electrons, and that's the double bond. So a double bond is a sigma bond, which is a normal single bond between the two nuclei, and then a pi bond, where you can have the electron above and below. Drawing the energy of that, typically the S or PZ, I've drawn it as a kind of weird combination here, really just to emphasize it doesn't matter which, but you get that overlap to give you the sigma, and then the PX and the PX overlap to give you the pi. So double bond, sigma bond, and a pi bond. And now for a triple bond, well, triple bond, you've got 6 electrons. So that means you must have 3 bonding orbitals to put those electrons in. So we'll have what we've done already. There's the blue sigma bond, that would be a normal single bond. One of the pi bonds is above and below. That's the overlap of the PX and the PX. Well, now the last bonding orbital is going to be the PY, which is going in and out, and the PY here going in and out, making the new pi orbital, which is above or in front of and behind the sigma bond. So sigma bond in the usual way, top pi from the PX's, in and out pi from the PY's. Looking at the energies there, SR S or PZ, whatever's giving rise to the sigma, the PX and the PY, which of course are effectively the same orbital, just different in orientation. So we got 1 electron in each of those, so 6 electrons, which we need for a triple bond, a sigma bond, and 2 pi bonds. Hopefully that made some sense. We'll come back to it a lot, triple bonds, when we talk about the alkynes. Much more significantly, much more in depth, we'll talk about the double bond when we get to the alkenes. Hope this made sense, and I will see you in the movies.